All right, so this is going to be our video on the introduction to kinetics. So this is from our lesson 1 of this booklet, and we're going to try this new method where you can see me, and we'll see how this goes. Okay, so in lesson 1 we were trying to accomplish a couple goals. We were trying to think about variables we can use to monitor reaction rate, formulating some definitions for a reaction rate in terms of rate units, and then also measuring the rate of a chemical reaction, and also determining the instantaneous rate of a reaction using the graphical analysis. So that means we're going to look at graphs. So here we go. We got chemical kinetics. This is a study of rate over time. Kinetics is this idea of movement. So we're talking about particles moving, and as particles move, that's going to be where the result of our chemistry. We've talked already in our introduction of this course about the idea that chemistry is chemical change. It's a change in the organization of chemicals. This is a change in potential energy, but this change in potential energy is caused by gains and losses of kinetic energy. So when we talk about chemical kinetics, we're interested in how fast those changes are occurring and what kind of energy exchanges are happening. So the rate of reaction is best described as the measure of the rate of chemical change over time, how quickly the chemical states is changing. There's a lot of factors that can affect chemical change, and there's also a lot of different ways that we can measure it. So we're given a very generic equation in our data, but this is just as some chemical reaction. Not all chemical reactions can be measured in the same way. Sometimes there's no significant change in color, for example. There's no change in mass. There's all sorts of different things that might not be applicable. So we've designed this theoretical example where we have some sort of solid mixed with something that's dissolved, and the result is some gas and some new solution plus some heat. So this means that if you are the observer of this experiment, since we can never really truly see particles actually moving, we can't actually sit down and watch them, we can't see how these two particles are colliding and how fast that's happening. There's no camera taking pictures, which is how you would measure rate with something physical, like a big object, like a car. If we're trying to measure how fast the car is going, we can measure how often the tires are turning. But here we can't see the parts. So because you can't see the parts, we have to look at what the effects are. What effect are we seeing from these parts that are moving? So for example, you could measure the change in temperature over time. And because this chemical reaction produces heat, then the temperature will change, and it will change proportional to the amount of chemical reaction that's happened. And that's sort of the key. We could also think about how we have a gas here, right? So if we have a gas, then that means that as the gas is produced, there will be an increase in pressure. If this chemical reaction was happening in a test tube, you could put your thumb over the test tube and you would feel the pressure of the gas on your thumb. If you were here for the magnesium experiment, we did this in class where we added some magnesium to hydrochloric acid, shook it up, put your thumb over top, and you could feel the pressure. You could even light that pressure on fire. We could also put this whole thing on a scale, and we could consider the mass change over time, because only part of the material is staying in the vessel. The gas is actually going to leave. So provided all of the gas is leaving, then measuring how much the mass is getting lighter over time tells you how much product you've made. And finally, with this experiment, you could also measure the color change over time, because we do have two different colors. We have a blue compound, or a green compound, and a red compound. Then over time the color would change. This one's very difficult to do in our current setup at school. We don't really have a spectrophotometer, but this is a really common strategy at university and in labs. Spectrophotometers are these machines that shine light, and then you put a little vessel in between where the light is being shone, and the light passing through will be absorbed by the color. And the more intense the color, the more light that's absorbed, and the less the meter will go down. And we can use that to measure it. So once you have a measurement, and you take those measurements at certain time intervals, then you can calculate a rate. And so rate is a measure of the total change in concentration of a reactant or product over a specific time period. So we're looking for a change in concentration. That's what these square brackets mean. These are concentration brackets in chemistry, and over a time. And I usually use a little sort of curly T to represent the variable time. If we're thinking about change, then change is usually found, so the change in something is found by finding the final value minus the initial value. If you've taken any physics, then this is a very common calculation to do. If you've done some math even, and when we do rise over run, we often take y2 minus y1, or x2 minus x1 for the run. So sometimes you might refer them as T2 and T1. I like final and initial because it's a little bit more specific or more general. And so there you go. So the average rate is then equivalent to the slope here. This is the same equation as slope. Remember, I'm going to do a little slope is equal to the change in rise over the change in run. And so this is my little thought bubble here. So that's our thought in the back of our minds, that if you've done any slope calculations in your math classes, this is the same process. So we're looking at a graph that's going to be going to have concentration over here. It's going to have time over here. There's going to be some data points like this, and then we're going to find a line that goes through them, and we're going to find 2 points on that line, and we're going to find the rate. And so the rate will be the ratio here. This is going to be rate in this way. Okay, so we can do this. Here's an example question we worked through in class. Here we have the time. We have a set of times here, and we have a set of concentrations. So we could plot out this data on a graph, and we did this in class. The data looks sort of like this. Typically the data kind of curves off for data like this, but if we want to find our average rate over the 50 seconds, we're going to take our data point from 0 and our data point from 50, and we're going to find that slope. And so we did that here. We find that over here, sort of thing. We take the difference, we divide it by the difference in time, and we end up with a value of 0.0134 molarity per seconds. Remember that molarity is moles per liter. So it's a measure of how many particles in a given liter. Moles is just a number. It's a number of particles. So what is the average rate over a different interval? We can take a different interval, and because our graph goes in a sort of angle like this, typically if we find a different interval, so this was 20 to 40, we would actually find the rate is a little different. Sometimes a little faster, sometimes a little slower. The larger the time interval, the more average the rate you're getting. Once again, take the difference in concentration, divide by the difference in time, and we end up with a new rate. So this tells us something, right? This gives us a little hint that in a chemical reaction, rate is not constant. There seems to be some sort of dependent factor that controls rate. And this will become a very important key point as we go forward. So once we get into our equilibrium unit, we're going to talk a lot about how rate of a forward reaction starts to slow down over time. So the rate we're going to also refer to our rates always in the positive. This can be a little bit confusing, but if you have something that's being consumed, we're still going to use a positive rate value, even though when you do the math comes out as a negative value. And so this is because time moves forward, and so we want to use a sort of a positive value for doing this discussion. So here's my final statement for this question, where I had a negative molarity per second change. I described it as in positive terms by referring to the consumption, and the consumption indicates that the amount of this C4H9Cl is being reduced. So here's my little statement on that. The rate of chemical reaction is always positive. It can be confusing because the rate of disappearance is negative relative to the rate of formation, but the rate should always be reported in the positive. It's trying to refer to something changing over time. I don't like this as much. I like to think mathematically. I like thinking about, I can understand a negative number. I don't like the extra words, but this is something that we do in chemistry for whatever reason. Somebody decided this was the reason, this is the way we had to do it, so you're stuck with positive values for your rates. All right. Now, if you do the rates of two different chemicals in a chemical reaction, so like this one, we found that there were two values we could get. We could get a rate of 1.75 for either the NO or the NO2, but the rate of O2 over here was half of that. And so when we look at our chemical reaction, we notice that in the chemical reaction, the stoichiometry ratio is 2 to 1. So that 2 to 1 ratio means that we only create half as much oxygen for every NO2. So if you know the rate of consumption of NO2, then the rate of O2 formation is half of that. It's a 1 to 2 ratio. So this is a really important observation, that stoichiometry has a very important relationship with rate. So there are some practice ones, practice example questions here that you can do. We did the first one together. I just want to go through this last section here, which is the change in rate over time. Generally, the change in rate over time is going to move in a non-linear manner. Somewhat logarithmically is probably a good approximation here. It's usually going towards some sort of maximum value. But an interesting part about rate is that chemical reactions, they essentially cannot stop. They will reach some sort of minimum, but they can't actually reach their maximum. It's what we call an asymptote in mathematics. So it will keep reaching, but it'll never reach infinity, or it'll never reach zero. You'll never be able to have you'll never have a container that has 100% of one thing or 0% of another thing. There'll always be 99 point, who knows, maybe it's 99.9999. In some other examples, like we'll talk about in a following unit, equilibrium, you're actually going to have situations where you have 50-50, 50% product, 50% reactant, where the reaction slows to the point where you still have reactant that's not being consumed. If we were interested in finding an instantaneous rate, this can be useful to compare two reactions, to think about which one is the more aggressive reaction, for example. Then what we would want to do is we want to pick the rate at a single point. And so instead of finding the average over 2 points like this, if we wanted the instantaneous rate, we would want to start moving this second point. So I'm going to get rid of this. Move this second point closer and closer and closer until they're right on top of each other, and then that would be the rate of a single point. This is called this is what one of the reasons for doing derivations. This is a calculus concept. The idea that what is the slope at a single point, and one of the ways to do this is to use what is called a tangent. So this is a tangent to the curve. Essentially, on your curve, if it's truly curved, then there's only a single line that can cross through any given point without crossing through any of the other points on the line. It's going to be a pretty tricky concept, but the idea is that if this is the point you're interested in, you can only draw one line that will cross through that point without touching anywhere else on the line. So I can kind of stick my point right there. So this will be the tangent for this point. If I can find the slope of this point of this graph, then this will be the rate at this point. Rate at point. Let's just call this B, point B. And then over here, this is a little bit messier one, but if I draw a point here, then there's also only one straight line that I can draw that will not touch any other points on this curve. So I'm going to try to see if I drew the line here, it would go through more than one point. So I'm trying my best to draw something like this. Tangents are very difficult to draw. We actually typically nowadays don't draw them at all. We get computers to do this for us. That's the better way to do this process, or to use calculus. And this would be the rate at A, and we'll just call this A. And so we could compare the slopes of the rate at A and the rate at B, and that's how we would find how the rate is changing over time. So I'm going to just make little arrows here. This is going to be my tangents. These are tangents. So finding the tangent, let's maybe write a little note for ourselves. We'll go through this on Monday. Finding the tangent at a point allows for determination of the rate at that point. Analyzing many tangents along the curve. Curve allows for the study of how the rate is changing. Oh, didn't like that. Changing. And that could be useful. If you're designing a chemical reaction that's going to be happening, let's say I'm designing a chemical reaction for a school project or something. I don't really want to design it around a reaction that has a very high change in rate. If the rate goes from very quick to very slow, that means that as soon as you mix the two chemicals together, they will instantaneously react, and it could be very violent. So an explosive, for example, probably has a curve that looks something like this. The reaction probably happens really, really rapidly at the first, and then it slows down immediately. But by that point, most of the product has been consumed. If you were to look at something like rusting of your car, your rusting of your car is probably a very slow process. And so the rate starts slow and it continues to get slower over time. But at that point, it's probably spread to a different part of your car. So, and you might be interested in exploring methods that would even slow that rate even more, so that we could slow the rate of rusting to the point where it doesn't happen. So that would be kind of the idea of comparing rates. You can also do these nearly instantaneous rates by finding the rate at any 2 points. So you could compare 2 points, and that would also give you an approximate rate as well. But the tangent method is really the way to get the rate at a single point. All right, so we have some more practice questions. I'll try to fill these out and post them online, but otherwise we'll see you back for the next video on the rate and stoichiometry lesson. So this is going to be our video on the introduction to kinetics. So this is from our lesson chemical reaction. The stoichiometry of the stoichiometry ratio is 2 to 1. So that 2 to 1 ratio means that we only create half as much oxygen for every NO2. So if you know the rate of consumption of NO2, then the rate of for doing derivations, this is a calculus concept, the idea that what is the slope at a single point. And one of the ways to do this is to use what is called a tangent. So this is a tangent to the curve. Essentially, on your curve, if it's truly curved, then there's only a single line that can cross through any given point without crossing through any of the other points on the line. It's going to be a pretty tricky concept, but the idea is that if this is the point you're interested in, you can only draw one line that will cross through that point without touching anywhere else on the line. So I can kind of stick my point right there. So this will be the tangent for this point. If I can find the slope of this point of this graph, then this will be the rate at this point. Rate at point. Let's just call this B, point B. And then over here, though this is a little bit messier one, but if I draw a point here, then there's also only one straight line that I can draw that will not touch any other points on this curve. So I'm going to try to see if I drew the line here, it would go through